All right, today we are starting Unit 3, which is all about polynomials. And we've worked with these a little bit, obviously, up until today, but today we're getting into some of the more complicated ones. And we're going to be doing a lot of different things with them. So polynomials, there's three main targets in this unit. The first is we're just working with different operations, specifically in regards to exponents. So today is pretty much primarily about different types of exponent properties. But target 2 is really going to be about graphing different sized polynomials. And then target 3 is all about finding different zeros of those. So let's get into the main part of today. And again, we're going to talk about properties of exponents. So before we get started, if you guys could all pause your video, I would love it if you would try the 2 review problems at the top of the page. All right, answers. Question 1, if I do 5 to the third, exponents, the idea of really any exponent is that, again, they take the number that's on the bottom, called the base, and they multiply it by itself this many times. So the exponent is really never the number that's involved. That just tells you how many times to multiply the number that's being raised to that number. So if I say 5 to the third, it just means I'm going to do 5 times 5 times 5, which leaves us with an answer of 125. Even if we get to something a little bit more complicated, we still have something in the middle that's being squared, which just means for us that we're taking 3 squared and we're multiplying it by itself twice. 3 squared is the same thing as 3 squared times 3 squared. And we know what 3 squared is. 3 times 3 ends up being 9. So 9 times 9 ends up being 81, which is our final answer. So exponents really kind of follow a lot of those main rules. Now, I will say a lot of what we're going to do today, there's a lot of different rules that we're going to cover. Almost all of them are review from Algebra 1. There's only really 2 new ones that we're really going to talk about a little bit more in depth. Never mind. I think you guys actually covered almost all of these. So these are not things that you're going to have to necessarily memorize, but you are going to want to have this sheet kind of with you when you go ahead and are doing your homework. So the first rule that we're going to talk about is called the product of powers. Basically what this rule says, it says if you have basically any number that's being raised to a power, so let's say a raised to the third, times b, another number raised to the fourth, or not another number, a to the fourth, it pretty much just means as long as whatever the base is, in terms of simplifying, when you have a product of powers, that's the same thing as when we add the exponents together. So all of this at the end of the day is really going to simplify, and it's going to become a to the 7th. And the main reason why is because think about this. If I expand this, a to the third ends up being a times a times a. A to the fourth ends up being a times a times a times a, which leaves us with really a total of 7 a's. So these rules, essentially what they are, they're going to end up being kind of shortcuts in a way. So a to the third times a to the fourth, the shortcut in place of writing out all those a's is we just add the exponents together and you're left with your final answer of a to the 7th. Now, power of a power is exactly like it sounds. It's when you take something that's being raised to a power and you're raising it to a power. So when I take, for example, let's say it's a to the third, and I'm going to raise it to another power. Now, here's where it's a little bit different. Technically, if I'm going to have a cubed raised to the fourth, we would take all of those pieces, that a to the third, and we would multiply it by itself 4 times, which then we'd be kind of back at our product of powers. If I have 3 a's here times 3 more here times 3 more here times 3 more here, technically we have a total of 12 a's. So the shortcut in terms of power to a power means we take the exponents and we multiply them together, and this would become a to the 12th. Okay. Now, it is possible power of a product. It is possible to be raising multiple things to a different power. So let's say we have two different numbers. Let's say we have like an a to the third and a different number that's a, I don't know, b squared. And I'm raising those to the fourth power. What that tells us is, again, we still just apply the power, the product of a power rule. I'm going to multiply this exponent to each of the exponents that are there. Exponents only get multiplied to exponents. They never get multiplied to a number that's a base. So at the end of the day, this would simplify as a to the 12th and b to the 8th. Okay? Now, negative exponents, this is kind of one of the weirder properties. if you go to your calculator and type in 2 to like the negative first, for example, ooh, my 2 went crazy. 2 to the negative first, it actually gives you 1/2 as an answer. And the reason why is because what negative exponents do is they move numbers to the opposite side of the fraction. So if I have 2 to the negative first, what it did was it moved this 2 to, oops, nope, it moved it to the bottom of the fraction. So that's really no different anytime you have a number. If you have any number being raised to any negative exponent, what it's going to do, it's going to move it to the opposite side of the fraction. So if it's on the numerator, it would move it to the denominator. Or if you had, for example, 1 over a squared, the negative 2a to the negative second power, it would move the number that's on the denominator. It's going to move that a squared up to the numerator. Okay. Now, zero exponent rule is Miss Hardy's favorite, actually, because it's one of the most simple rules that are out there. If you have any number and you're raising it to the 0 power. So what's cool is if I go to my calculator, hold on. Nope, I forgot. Miss Hardy has the new calculator app. Haha. But so if you go to your calculator, which is not up, hold on a second, guys. If I go to, let's see, third time's a charm. If I go to my handy dandy trusty calculator and I type in any number raised to the 0 power. So if I go 5 raised to the 0 power, if you check that out, you're going to notice that it gives you 1. And if I do it with really anything, if I do negative 102, oops. If I do negative 102 and I raise that to the 0 power, surprise, surprise, we get 1. Any number raised to the 0 power is always going to reduce to a value of 1. And that's true of any number that you would choose to raise to that power. So in exponent world, that just means if I take any number, let's just use again base of a, and I raise it to the 0 power, the answer to that question is always 1. Now, quotient of powers is kind of like the opposite of product of powers. The only difference here is that quotient means divide. So, for example, if I'm taking, for example, like a to the third over a to the fourth. If you have two bases that are the same on both the numerator and denominator, instead of like what we do in product of powers where we add the exponents, if we're having a quotient, what we do is we subtract. It's the top number minus the bottom number. And we're left with 3 minus 4 ends up being negative 1. Now, something we're going to talk about in just a little bit, but one requirement of all of your final answers in this unit, all of them are going to be simplified, but negative exponents are actually not technically considered simplified. So as a final step, we would take that a and we would move it to the denominator, and that would be our final answer. Okay, so last but not least, power of a quotient. This is very similar to the product of a quotient, but or power of a product. But at the end of the day, it just means if I'm taking two variables, let's say we have a and b, and I'm raising a quotient to a power, it just means the same thing. You're going to take each of the pieces that are on the inside, and we're going to multiply the exponents together. Final answer would be a to the 20th over b to, oh, that was supposed to be a 6. It also looks like a b. It's b to the 6. Bad number. Actually, it is a B. Let's fix that. That's going to be bad. That's a little bit better. Okay. So at the end of the day, the goal really for the rest of today is that we're going to be just simplifying different types of exponents or expressions that involve exponents. So there's always two things that you have to keep in mind for your final answer. First of that is all exponents have to be positive. So if you have a negative exponent somewhere in your problem, it just means you have to move it to the other side of the fraction and then simplify. And last but not least, it means all like bases have to be combined. So like you're going to see some of the problems we're going to deal with in just a little bit. When we say like bases have to be combined, in problem 6, for example, there's only two bases. Base just means the number that's being raised to the power. So if you'll notice, I have a G and a W and a W, G, G, W, G, W. All of those are either a G being raised to a power or a W being raised to the power, which just means for us at the end of the day, we can rewrite this so there's only one G and there's only one W. Now, we'll get there in just a moment and we'll finish that one together, but let's start basic. Let's start with number 1. So here we have 3 to the 3rd times 3 to the 4th times 3 to the 5th. Now, could you go the long route and write all of those out? Sure. 3 to the 3rd would be 3 times 3 times 3. 3 to the 4th, not 4, 3 raised to the 4th means 3 multiplied by itself 4 times. And then we would do 3 5 more times. And we could count up how many 3s we have. But the shortcut just means we're going to use, or the power, or the, oh my gosh, I can't talk today, guys. The power of a product to power rule, tells us that if I'm multiplying exponents that have like bases, all we have to do is add all of my exponents together. I have 3 3s in the first one, I have 4 3s in the second one, I have 5 3s in the third one, which means if I add all of those together, we're left with 12 3s. Now, some of the numbers that we deal with in this unit are going to be pretty large. You can either leave it as 3 to the 12th if you really want to, or you could actually tell me what it actually equals. It's a little obnoxious on this one, but it's 531,441. Either answer in this case would be acceptable. Some of the numbers that we get, if it's really large, you can leave it as just 3 to the 12th. But number 2 is my favorite one on this whole worksheet because any number raised to the 0 power is 1. I don't even have to do any work on this one. Now, number 3, this is a classic example of our product or our power of a quotient. We have 2 numbers on the inside, both of which it might help to notice that they're technically being raised to the first power. So if we are going to simplify this, we have to multiply whatever power is on the outside to both of the powers on the inside. So on the numerator, 3 times 1 ends up being 3. And on the denominator, 3 times 1 ends up being 3. Which, these 2 numbers really aren't that bad, actually. So if I do 3 to the 3rd, 2 times 2 times 2 ends up being 8. And 7 times 7 times 7 ends up being 343, which doesn't reduce. So final answer is 8 divided by 343. Now they are going to get gradually harder, but even if you have multiple powers that are being raised, it's still considered the same as the power of the power of a power rule. So which tells us that any numbers that are in the exponents, if all of these are being raised in sets of parentheses getting larger and larger and larger, it just means at the end of the day that those all get multiplied together. I would do 1 times 3 times 5, which really ends up just being 4 to the, why am I doing that? 4 to the 15th, and we are done. That number's really kind of large, so I'm going to leave it as 4 to the 15th. Because you do it, sure. You could do 4 to the 15th, but I'm going to leave it as such. Now, even if you have negatives involved, simply because of the fact that what's inside of the parentheses here is a -8, and what's inside of the parentheses here is a -8 also, your base is the same. Which technically just means I have a total, if I have 1 -8 here and 4 -8s here, we have a total of 5 -8s. Now, this one actually isn't too bad. If you multiply this out, -8 to the 5th, This ends up being negative 300, 32,000, excuse me. 32,000, why did I have a 4 in there? 32,768. There we go. Having trouble writing today, guys. Whew. All right, now let's look at this monstrosity. Now, it looks obnoxious, but I put it in here for a reason. Some of the problems that we're going to deal with today look pretty bad, but they actually simplify really nicely. So usually as kind of a first step, any numbers that are on the same side of the fraction, and we don't even have a fraction in this one, I'm going to start by kind of focusing on one of those bases. So let's say we focus on just the G base. What we're going to do is we're going to look at any of the terms that have a G in it. And what we're going to do, they're all technically just being multiplied together, which really just means for us at the end of the day that we're going to add all the exponents together. 3 plus 2 plus negative 6 plus 5. And we're left with a G to the 4th. So as ugly as all of that is, all of it combines really to be something pretty simple. And we can do the same thing with the other base, the W. We have a couple different terms that have W's, right? We have a 7, we have a negative 9, we have a 2, and we have a negative 6. All of those exponents we're going to add together as well. 7 plus negative 9 plus negative 6, and then, plus 2 plus negative 6. And we can simplify that as well. If we add all of those together, those actually add up to be negative 6. Now, this is what we mean when we talk about final answers. This actually isn't considered simplified because we've broken one of the golden rules, and that is that all exponents have to be positive. So there's a pretty easy way to get rid of this W to the negative 6. And there's a way to change the negative exponent to be positive. And all it means is, right now it's on the numerator of the fraction. It just means to make it positive, we're going to move it to the denominator of the fraction. Now, G didn't have a negative exponent, so that's just going to stay. Ooh, I'm sorry, wrong button. That just means I'm going to keep the G to the 4th on the numerator, and just the W, just the piece with the negative exponent is going to move to the denominator. Now, I can't combine these because I can't do 4 minus 6 in this case because my bases are different. You can only really combine things that have like bases, so that's about as simplified as we can get. So what I want you guys to do right now, I want you guys to pause your video, and I want you guys to give example 7 a shot. All right, answer is up. You should have gotten as your final answer, you should have got C to the 50th and times K to the 85th. Now, this one seems a little bit obnoxious, but at the beginning, you just had one extra step because everything that was inside here, all of these numbers were being raised to the 5th power. So our first step was we had to distribute really that 5 to each of the exponents. I always think of it as like a normal distributing. It's just that 5, since it's in an exponent, it gets multiplied to each base's exponent. So that 5 is going to be multiplied to the 3. It's going to be multiplied to the 9, to the 8, to the 2, even to exponents that always aren't written. If you have a variable being raised to the 1st, don't forget to multiply to that one as well. This C is still being raised to the 5th power. It's still inside of the parentheses. So we can't forget to, we don't want to leave that guy out as well. And then last but not least, multiply the 5 times the 4. So once you do that, you're left with these pieces right here. And then we're right back where we were in example 6. We're going to take each of our like bases and add up those like exponents. So to get our final answer, C to the 50th, all I did was take 15 times 10 times 5 times 20. And to get to the 85th, the K to the 85th, all I did was add the 2 exponents for K, and we got our final answer that way. Okay. Now, most of the problems, they're not all going to be this simple. Sometimes they're going to be a little bit more involved. And this is where it's kind of, some students like to do this in different ways. A lot of times what I will do is, especially on problems like this where yes, it's being raised to an exponent right here, but before I start dealing with the power to a power, I like to simplify what's inside. Because something that I'm noticing is that I have a lot of like bases. I have W's here, 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 and here. And I also have P's here and here. So there's really only 2 bases that I see here. So that's something that I think I'm going to do first on this one. I'm going to leave the exponent on the top alone first, and I'm just going to simplify a little bit with what's inside. So let's start with my numerator. Now on the top, there's no other numbers on the top, so I'm going to keep the 4 there. But I do only see, I see W's up there and I see P's, which means I can simplify all of the W's together first. So if I have 4 W's here and I'm taking away 2 of those W's, technically I just have 2 W's here. And P's, there's no other P's at the top, so that's just going to stay a P to the 3rd. Now, on the bottom, there is a 2 on the bottom, so that's going to stay. P's, there's also still only 3, so I'm going to align them over here. W's, on the other hand, we have 3 here, and I'm taking away 8 of them. So 3 minus 8 really ends up being -5. So if you're a fan, a lot of times I'll simplify what's on the inside first, because then once I raise everything to the 3rd, we're pretty much done. Now there is a 3rd thing that we can simplify though, other than just all of our W's and our P's. Something else that I'm noticing is we have a set of numbers. Since these numbers are both on the inside, we can simplify them just like we would normal fractions. So one of the other steps that we can do is I can actually do 4 divided by 2, which really just ends up being 2 over 1, but I'm not going to write the 1. There is something else though that I see that's not considered simplified at the end of the day anyways, and it shows up right here. We do not like having negative exponents. So what's going to happen is this W to the -5th, it's basically going to move to the top and it's going to become positive. And what happens is here is actually all of my W's, I have more W's on the top technically. If I have 2 W's on top and I'm adding 5 more, technically we have 7 total W's. Now, we also have P's in 2 different places. Now here, they're on opposite sides of the fraction. If I have 3 P's on top and I have 3 on the bottom, what we would do is we would simplify them together. We would take the numerator and subtract the denominator. But this is something kind of odd. 3 minus 3 really ends up being 0. And P to the 0 power just ends up being 1. So actually what happens, my P's cancel out completely. It's kind of like if I had a 2 on top and a 2 on the bottom, 2 divided by 2 ends up being 1. The same thing is true here. If I have 3 P's, technically if I have 3 P's on top and I have 3 on the bottom, each one of them are going to cancel. P divided by P is 1. P divided by P is 1. P divided by P is 1. And all of them cancel. So really all we're left with is 2 times W to the 7th cubed. All of this grossness really simplified down to this right here. And now there's actually nothing else that I can simplify. I can't do 2 times W to the 7th because I don't know what W is. But that just means my last step is going to be to now multiply the 3 to each one of those exponents. 2 raised to the 3rd power. W, 3 times 7 ends up being 21. And sometimes we will leave this as our answer, but 2 to the 3rd is actually pretty nice. 2 times 2 times 2 really ends up being 8. Bring down the W to the 21st. And there's no negative exponents, so that's our simplified answer. Okay. So, example 9, this one I made a little bit easier in the sense that you don't really have to distribute anything, but I do want you guys to pause your video and try number 9 on your own right now. All right, final answer. You should have f to the 4th over 8x to the 7th. Now, let's see how we got that. Now, I will say, guys, when it comes to simplifying, there's honestly so many routes that you can take on this. Like I kind of mentioned before, a lot of times when I simplify, I try and take it in steps. That way, if you make a mistake, you can kind of work your way backwards. So the first thing that I did was I combined all like terms that were on the same side. So like I looked at all the numerator, all the x values. I started with x, and I looked at all of the places that there was x's in the numerator. And all I did was I added all of those exponents together. So if I took 4 plus 1 plus -8, you end up getting -3. So just to kind of simplify it and make it so there's not as many variables, I did all of that as my first step. And I did that with each of the variables. So the f's, there's 8 of them here, and there's -6 of them here. So 8 minus 6 ends up being 2. On the bottom, we had -5x's here and 9. So if I add those, we get x to the 4th. And for my f's, I had f to the 0 here, which really ends up being just 1. We can ignore that one. So that f to the -2 just stays. Now the numbers, if they can simplify, you can do that right now. You don't have to worry about exponents on these because they both have an exponent of 1. 2 divided by 16 just ends up being 1/8. So once you tackle that, then it's really a matter of putting numbers. Remember, we're not allowed to have negative exponents. So what I did is I moved the negative exponents to their correct side. So this x to the -3rd, we're not allowed to have negatives on negative exponents, so I moved it to the other side of the fraction. And I did the same with this f, because on the denominator, that one has an exponent of -2, so that f to the -2nd is going to move to the numerator. And this is where we would be at. Now that all of your terms are now positive, now just one last simplifying step. We have 4 f's here, which is how I got f to the 4th. And on the bottom, there's a total of 7 x's being multiplied together, which stays. Okay? So a lot of times it's really just taking it step by step and then using each of the properties that we see. Now, I figured we do one problem that involves a little bit more complicated stuff, but this one actually is easier than the last 2 problems combined. If it says find the surface area, don't worry, I'm not gonna make you actually find the surface area of the sphere. All I'm gonna look for you to do is use the formula. It says the surface area of a sphere is 4 pi r squared. So remember, the radius of a sphere goes from the center all the way to the edge. And they're telling me that x/3 is the radius of that sphere. So that is going to be what gets plugged into, not pi, sorry. That's what gets plugged into the radius spot. And all I'm looking for you to do is really just simplify this side. So in terms of simplifying, let's see. Inside of these parentheses here, I'm raising all of that to the 2nd power. So my first step is probably going to be to multiply that out. Both of these have an exponent of 1, so I'm going to raise both of those pieces to the 2nd power. So it's going to become x to the 2nd over 3 squared, or I'm just going to rewrite that right now. 3 squared is going to end up being 9. And now it's just a matter of combining kind of some of the like terms. Technically, this divided by 9, a lot of times what they'll do is they'll put the numbers together. So we'll leave 4 on the numerator, 9 is going to go to the denominator, and then the pi and the x squared stay. Ooh, added a line. Final answer, surface area is 4/3 pi x squared. So we're not going to go crazy with a lot of the formulas. A lot of times it's just going to involve simplifying them. So if you want to give the You Try Nows a shot, go right ahead. If not, we are going to go over some of these in class. So make sure if you have any questions, you have those at the ready. All right, guys, thanks. Have a fabulous day, and I will talk to you guys in a bit.